Just assume everybody's here. So let's continue. I think it's a good, yeah, to say that this was the first half. Now we come to the second half, and the second half is about the publication. And I told you already, we have a fluorescent FRET biosensor, and the publication basically is about a fluorescent FRET biosensor with a very specific application. And this is for real-time profiling of cell membrane protease function. Yeah. So when I go through this process now with you all together, then you need to start on the bottom right, top right. And again, we will start to identify where are our donor and where the acceptor. So we actually have in our legacy on the right side, we have our donor twice, because one time we have it here. And the second time we have it, it's already green, so we'll just not do it this way. I will just mark it with a D here on the bottom. This is our donor. First time it's separate, as you will see, later Y, and second time it's just there, it's connected. And GFP means green fluorescent protein. Our acceptor is here. The name of the acceptor is TAMRA. In the legacy, we call it peptide because we have a combination. So first we have our acceptor, but also part of the donor and something in the middle to connect them. So yeah, peptide is the name there. The name of the acceptor by itself is TAMRA, and you will later need this, but I will mention it later on. Okay. We have also the legacy fluorine and MIP, what is a membrane inserting peptide. We needed to connect our FRET pair to the cell. Let's start on the top right first. So what you can see there is that we have separated the acceptor and donor in the test. And what we want to know now, we want to assemble them. When we assemble them, FRET is happening. And now what we can see, okay, that the acceptor is lighting up, or basically giving us a signal, because we have the excitation from outside. FRET is happening, okay. Now, and that's why we need the MIP, membrane inserting peptide. We connect them to a cell, or the connection is basically happening by itself. And when the cell is next to them, basically the membrane inserting peptide helps our FRET pair to connect to them. And what we have there is we have a collaborate site between the acceptor and the donor. Okay? So some point where we basically can cut the connection. And the connection that is basically cut is happening because of hydrolyzation, what is provoked by fluorine. And when we want to know something from our biosensor now, we exactly want to know that, okay, when is hydrolyzation happening? Because this is basically fluorine activity. So when fluorine is active, then the connection gets cut. And now this is happening, what we mentioned before in our simulation, but also before. Remember the scissors? When the scissors are now open, we basically get a signal from our donor, and this is what's happening on the bottom right. And when they are, on the beginning, before the hydrolyzation happens, they are closed. And then basically, we know something about fluorine. And this is what is this specific biosensor also about. So developed biosensor by the publication is doing that. It tries to find out, okay, how is the activity and how we can, and this is how we can figure out what is happening. And this is also very important because we can then see something about a living cell. And this in real time, and we can use it for different applications. The publication by itself not just presenting the process, obviously, because they develop the biosensor. So what they're doing there is they go in details about the assemble, the energy efficiency, and the intensity of a single part of the biosensor with fluorine. It gives us some experiments that they done, some tests about like how the developed biosensor works with fluorine in general. And they also give us insights about the orientation. Why is the orientation important, and is it's still working that the orientation of our donor and the acceptor is in the right way, so we get a connection to the cell. Is this happening? We get some insights of the anchoring process. So is the MIP doing his job, if you want to say it this way, about the amount, the concentration of how much biosensor we need for how much cells, and speed, stability, and of course, very important to not damaging the cells. So the publication tries to prove that the biosensor work how it's supposed to work. And I want to give you one insight to one of the last experiments that they done, because what they done there is they tested first, okay, we have different cells and how is the fluorine activity there? Because of course, when we want to prove something about we can sense the fluorine activity, we need one cell that is very good in having fluorine activated, and this is U251. So they tested another one just to test it. But here, what you can see here, they used the one that works. So U251 is the cell. And now what they tested is they incubated the cell with our biosensor. And what we have here on the top is we have our donor, we have our acceptor, and they, after a certain amount of time, they washed. So basically what we're expecting is exactly that this cutting procedure is happening after the done. So what we're expecting is that the signal of our donor will be stronger and stronger. And you can't see it on the rows with the donor and acceptor, but you can see it on the ratio. And you can also very good see it on the diagram B, where you see basically the ratio of GFP to TAMRA. Like I said, TAMRA is the acceptor, GFP is the donor, and it's basically raising. So the signal of the donor is getting stronger and stronger, of TAMRA is getting lower, and that's why we can, or they, so my work, they proved that it's working how it's supposed to do. And just to remember, the important aspect really about fluorine is that it's important when it comes to the application of disease, working with disease, how are they activated or not. So what they basically have with the biosensor, they have something to prove that a disease is activated or not, in a very general way said. So let's conclude with a discussion. This publication is in detail about one fluorescent FRET biosensor for protease imaging with very helpful diagrams. They go into detail. I have attached the important diagrams on the end of this presentation. I can't use all of them here, but I attached them because they are really helpful to understand the different experiments and how they progressed. They mentioned a lot of universal applications. For my opinion, I have to say that sometimes I felt like I need a bit more detail to really understand why this application, how we can use it for this application. They mentioned them, but it's just my opinion. I just would like to know a little bit more in detail how it works. Yeah, and the last point for me is just that I want to focus that they used here FRET with fluorophores. You can also use it with phosphorophores or other material that use luminescence. Yeah, I just want to say that in the end, and I think now it's time to show the sources and picture sources, and like I said, some Dutch diagrams, figures in the end, but thank you for now.
Thank you.
Thank you very much.